and another independent. And we discovered that at the end of the day we need a line that tells us that relationship. And that line is best described by y is equals to mx plus c, where y is the value that has been output by the model, x is the input, m is the slope, b can be bias or intercept for this case. So what we want us to do in this case now for today is to discover logistic regression. Now under linear regression, we discovered that the values can be anything. For example, if I wanted to predict um, the cost of a house, for example, I've been given that of the cost of various houses, and I have variables such as the size of the house, where it is located, how big it is, how many floors it is, does it have a basement, who lives in there, and is it in an urban area, is it in a village, is it in a suburb, sort of, is it near a lake, what physical features are close to it, does it have access to electricity, does it have access to water. So all those things determine the price of the house. So imagine I have various, so many houses, their prices and their characteristics. So then I'm able to get a relationship between the characteristics of the houses and the what and the price, right? So that's what linear regression does. So it's able to predict for us a house, for example, that we don't know the price, but we have the characteristics. So the price can be let's say 3 million Uganda shillings, 100 million Uganda shillings, 1 billion, depending. But now today we're going to look at the logistic regression. Now what logistic regression does is it turns those values into a probability, right? So we want a number that lies between 0 and 1. Let me give you an example. Why are we doing this? Because in most cases you might want to classify, you might not want to know how much a house is. For example, the data might be different and you want to say let's say, let me give an example of, is this drug effective on certain group of people, let's say pregnant ladies. So you want either a yes or a no. So you want probability. You don't want how effective the drug is. You just want to know, is the drug effective. So you have to get a probability score, then classify it. So in cases as such, binary classification, we need probabilities such that we are able to cap them and say, if this, then this, right? So then for today, today we're going to look at logistic regression, and it helps us to solve that problem. So like I said, in linear regression, it was just a method of predicting a continuous numeric value based on one or more input features. Like I said, we have one y is equals to b0 plus b1 times x1. So the x's are weights, yeah, because various inputs have various weights. Where the land is located might have a different weight than the size of the land. If the land is in an urban area, no matter how big or small it is going to be expensive because it's in an urban area, then versus the size, right, in a village. So the weights are different. So like I said here, x1, x2 are the various input features, y is the value you're trying to predict, b0 is the intercept, b1 or bn. Also here b1 up to bn are the weights, then x's are the input features. You'll forgive me for that. So the problem is, what if the question isn't how much but which category? So that's where we come in and we classify instead of using the linear regression. So logistic regression is sort of a classification algorithm. It's used to predict the probability that an observation belongs to a particular class. Yes, like I've said, is the drug effective? Yes or no? That's what it helps us to do. So how it helps us to do that is we take the values that are given to us and we pass them via a sigmoid function. Now what a sigmoid function does is it squishes values between 0 and 1. So meaning if the value is too large, a positive number, it will approach 1. If it's too small, a number, it will approach 0, but it won't be 0 or 1 exactly. So when z is 0, p is 0.5 exactly. That's 1 knot. So this gives the model an S shape. If you plot it out on a graph, it will give it a characteristic X shape, right, between 0 and 1. So how do we turn a probability into a class? So I've gotten the probability from the sigmoid function, and now we need to know So now, like I said here, if P is greater than 0.5, then predict class 1 yes, otherwise 0. So the classes are yes or no, depending on the probabilities you're given. The 0.5 can change, can be if P is greater than 0.7. It depends on the hypothesis you're trying to do. So if you have an experiment and you're trying to, let's say, you're testing a drug on pregnant ladies or on people that, let's say, have HIV. So you're trying to test how effective this is. So you can give it a p-value and say if it surpasses this threshold value, then you do A. If it does any other value, it's B. So how the model lands. So there is what you call a cost function, or some people call it the loss function. And under this we have what called the mean squared error, and we use the log. Now remember, what we're doing is logistic regression. So how we are able to calculate the loss or the cost. So basically the loss is you have a predicted value and you have the true value. So the predicted value minus the true value gives us the loss, right, or the error. So now we are able to calculate that with the loss function, in this case the mean squared error. So there's the mean squared error, and it helps us do that. So you might be wondering now, what are the differences between linear regression and logistic regression? So linear regression, it predicts a continuous number. Like I said, if you're predicting the what the price of houses, right? So it can be 1 million USD, sorry, 1 million Uganda shillings. It can be 5 million. It can be 5,550,000. So it's a continuous number like price. It can also temperature.
Yeah.
Uh, Adrian, your mic. So then then for logistic, it predicts a category. It can be yes, no. It can be an email, spam or not spam. It can be anything, right? So then the output range is any real number, negative infinity to positive infinity for linear regression, and the probability in logistic is either from 0 to 1. The sigmoid function helps us squish, no matter how large the value is, it will fit into 0 and 1. The equation is correct for linear regression. It's a classic y is equals to bx plus c for this case, while this one, it's y is equals to 1 out of the sigmoid function. Basically is what is the characteristic here for logistic. Core function is a straight line, then is an S shape. Mean squared error is used in linear regression. Then log loss, or BCE, that's binary cross entropy, is used for logistic. So then the example questions here would be, what will the house sell for? It can be any value from 0 to minimum up to max, any real value, as long as it's a real value, a real number. Or will this house sell in 90 days or in 30 days? Yes or no. So those are the classes. So you can implement this. Let me see if I have this. I did something with Jupyter Notebook. Let me see if I can share that in a few.